Okay, the part 2 of this, to talk about it, I first have to basically take and create a function that you guys have not seen before. So this is the function right here. Capital F of x is equal to the integral from 0 to x of f of t dt. Let's decipher this for a second, because I need you to have a pretty good understanding of what this is saying before we move on to what the fundamental theorem part 2 actually says. I'm going to define this and call this an accumulation function. And what it is accumulating, you guys know what the word accumulate means.
Yes.
But accumulation function is a function that accumulates area. It accumulates area under the curve. Or I should probably say area between the curve and the x-axis. The input of this function is the upper limit of the integral. Got it? So as I increase the x values, I start to have more and more area. So here's a visual for this. Let's say that this function right here is f of t. And I'm using t here because I don't want t to be my input variable. T is kind of like a placeholder variable. In parametric equations that we did last semester, t is a parameter. It's just something right now that's just kind of there so I can create this integral. But the real function is the capital F of x, and the real input variable here is x. So what's happening is that this integral here is defining area between on the curve on the interval between x equals 0, which is right here, and x equals x, which is right here. And we have this area now between the curve and the x-axis. So as I take this and I slide it left and right, I either increase the amount of area or decrease the amount of area underneath the curve. It is possible to take x and move it left, so that if I keep it going left, I now have negative area because I'm crossing over and I'm doing an integral with the reverse limits, or with the limits where the lower is higher than the upper. But in any case, that's how this is operating. If my function were to do things like this and start moving around, then as I slide x left and right, I'd probably cross between area that's increasing, then area that's getting smaller, then area that's getting up again. It just depends on how the function goes. The important thing to know about this is that the input value is an upper limit on the interval of integration. So we're going to practice with this for just a little bit, just with the accumulation function. Capital of f of x is equal to the integral from 0 to x of the cosine of t dt. I'm defining this function, and I'm defining it as the accumulated area between 0 and x of the function cosine of t. You guys should know what the cosine of t looks like. You should know where it starts, where it ends, what a period looks like. Just the basics about cosine t. It's actually much more important to know that than it is to know about shiftings with cosine t or increase. Like all that you can kind of play out as you need, but you need to know what a basic cosine t graph looks like. You also need to know that if you're using a calculator on any of this, it must be in radians. Radians is the real number value. Cosine takes a real number and it outputs a real number. If you're in any sort of unit, what it's doing is it's changing the real number to something else. And it's doing that for you. So do not ever use degrees in this. And for those of you that are in physics and are kind of worried about this with the final exam, just be really, really careful that you're in whatever mode is appropriate for the course you're in. Okay, back to this. What I want to figure out is just these different values. We're going to do a t-chart. I want to find f of 0, f of pi over 4, f of 3 pi over 4, or we'll do 3 pi over 2, and f of 2 pi. Now, you can do this in one of two ways. For instance, I can just do x and f of x, capital F of x here. And a couple of these you guys should know right off the bat. For instance, you know when x is 0, the integral is Yep. The integral from, remember, you're plugging 0 in right here. 0. So if you start and end at the same limit, remember this is one of those properties of integrals that we did. Our integral is going to be 0. You also know what another x value should be. 2 pi is going to be 0 as well. Because the integral from 0 to 2 pi of cosine is going to be the one where you have the negative and positive area perfectly canceling each other out. One complete cycle of cosine. The other two you may want to evaluate. And you're going to do that by actually just kind of evaluating this integral. The integral of cosine of t is the sine of t. And that's going to be evaluated from 0 to t. So my capital F of x is actually just equal to the sine of x. It's technically the sine of x minus the sine of 0, but the sine of 0 is 0. So I get this value of the sine of x. And then we can do the other two. Pi over 4 is the sine of pi over 4, which is root 2 over 2. And the sine of 3 pi over 2 is Don't let the trig be the thing that slows you down. Think about the circle. Think about the y value at 3 pi over 2. We're down. We're like the most furthest down that we could possibly be. If you look at the graph, you can kind of see this a little bit. Sine of pi over 4 is going to be right here. So this area is root 2 over 2. 3 pi over 2 is when we get all the way down and I have the sort of maximum value down here. So it's just kind of a, actually, sorry, let me back up. It would be, so I'm starting here. This is pi, so root 2 over 2, pi over 4 would be like right there. And 3 pi over 2 would be right there, to where the positive and negative area perfectly cancel each other out. But in any case, that's kind of what's happening here. You have an accumulated area up to a particular point, or up to a particular x value. So that's essentially how an accumulation function works. It's not a hard concept. It's just a different way to think about what you've already done. The theorem that we're focusing on today is the second fundamental theorem of calculus. There are only two. And it states something that's going to seem really obvious, but is going to become incredibly important to use. If f is continuous on an open interval I, containing A, then for each x in the interval the derivative of f of x dx is equal to the derivative of the integral from a to x of f of t dt. Or sorry, I should not kill that first part. I should write that as the df, capital F. Or let's just do this first. So erase that entire first part. I wrote that later at some point. This is equal to f of x. And in kind of words, what I'm saying is the derivative of the integral is the function. I had not defined what capital F was, and I meant to put a capital F in there.
d over dx.
Now, the kind of way that I can show this is if f of x is an antiderivative of little f of x. And I can kind of just work through this a little bit. So I'm going to take this thing right here and say, all right, we're going to keep the d dx on the outside. Let's actually do the integral. So if I'm saying capital F of x is an antiderivative, then what I'm going to get is capital F of t evaluated from a to x, which I get derivative dx of f of x minus f of a. That's by the first fundamental theorem. What's the derivative of capital F of x? Little f of x. And what's the derivative of the constant f of a? One of the weirdest consequences of this is that your lower limit does not need to be 0. It can just be any constant. This is one that will trouble you for a little bit as you start to see how this kind of works. Yeah, the lower limit by this theorem can just be any constant. It doesn't need to be 0. Okay. All right, so first thing. A lot of the first early problems you're going to do are just going to be finding derivatives. So I'm going to do the derivative from 5 to x of root t cubed plus 5 dt. There's a hard way to do this and an easy way to do this. The hard way to do this is actually to evaluate the integral, plug x and 5 in, and then take the derivative again. But when you realize that that's unnecessary, you can actually skip right away to the end. What is this? So I'm going to drag this down. Paste. Let's put that right here. I'm going to block that off in some sort of pretty colors. Root what?
X cubed.
Yeah, root x cubed plus 5. That's it. Okay, freak out on me. Go for it.
What the heck? I don't even know what that is. Wow. That's just, how do you do that?
How about this? What you're going to do is you're going to take this, you're going to integrate it, you're going to substitute x in for t, and then you're going to take its derivative again. So you get the original thing again. Well, what about the 5? All right, so you're going to take the integral, plug 5 in, and then to take the derivative. But when you take the derivative after plugging 5 in, you are going to get 0. So by taking the derivative, that lower limit didn't matter. You just get the function. This is saying the derivative of the integral is the function itself. And in a way, this right here and this right here are acting in opposite of each other.
So isn't that kind of redundant though?
What?
How does that help us?
Allow us to get there.
Okay.
We will get there. This is still just a process you're learning at the moment.
Okay. Makes sense that the integral is the function.
One of the things, though, is that a lot of functions themselves, a lot of times you're given, and this is where it's, I mean, I'll verbally say this, you're sometimes given in word problems a rate of change. And one that just came up in a word problem that's the BC kids on an AP exam, there's a rate of change of people entering, like going into an auditorium. So there's a concert and like there's some sort of fair going on in a place, and like it shows you like the rate of change of people, or the rate of people entering the building is this, and the rate of people leaving the building is this. And so an integral of that is actually the number of people in there at a time. And you actually define a function based on the integral, and then you want to do a derivative of that to evaluate something else. So you need to know the derivative of that is the original function. There's a lot of weird places where that occurs, and I'm saying a lot. This will definitely appear at least once in a free response, and also several times in multiple choice. This is extremely, extremely important when it comes to calculus. Okay, let's do a derivative of this. So lower limit's pi over 2. Upper limit is x cubed. Cosine t dt. And I'm doing a derivative of this. And the parentheses should kind of give you a clue as to something that also needs to happen in this particular case. No, you can. I mean, you're doing the derivative as a substitution here. So if this was just an x, what would happen? It'd just be cosine x. It's not an x, it's cosine of x cubed, but, so then?
3x squared.
Yes. And that is the... So we had to do the 3x squared because of chain rule, but other than that, we just take care of the substitution and then we're okay.
So you don't even have to worry about the 5 or 2?
No, in fact, I'm going to show you with this example how this works. So we're going to do it the other way. This is going to be the long way. Yep. It's easy enough to do. What's the integral of cosine of t? Sine of t. I'm going to evaluate sine of t from pi over 2 to x cubed, which means I get the derivative of sine of x cubed minus sine of pi over 2, and now you're going to take a derivative again. What do you get?
3x squared times cosine.
Yep. Do you see it now?
Yeah.
Do you see why the lower limit doesn't matter? Do you see where the chain rule comes into play?
How do we have a...
So can you only do this one?
Hang on, Elise, and then Nate. Sorry. Nate, Elise?
We have a negative on the right, but then a multiplication sign on the left.
I have a negative on the right, so this is a negative here.
I mean, yeah, but it's a subtraction.
It's a subtraction right here. Yes, this is just a times. When you actually do the derivative of this right side, you're doing the derivative of sine of x cubed, which would be 3x squared times the derivative of sine is cosine
The sign of pi over 2.
minus 0.
Wait.
Okay, Leo?
So you
Sorry.
got the antiderivative and then you went back.
In this method on the right side, I did the antiderivative and then did the derivative. On the left side, I'm showing you don't even need to do that. We're going to want to use the left side because that uses the second fundamental theorem. Nate?
So can you only do this when you know when you input when you input the lower limit, it's going to be a constant?
We'll move on to problems that don't do that, but we'll still use the same process.
Yeah.
Alex?
Is the antiderivative the integral?
And a function has an unlimited number of antiderivatives. So when we say an antiderivative, we are generalizing to include like a plus c. An integral is a specific reference to like creating a function. They're synonymous, they're just different contexts. Like offend and insult are the same, but they have different connotations. Okay, let's move on. Somebody wake Max up.
You got it on video. That's your story.
Max, you need to stop staying up playing Fortnite, which is now going to date this video because in 3 years or 4 years when people like watch this, they'll be like, oh, people were doing that back then. That's hilarious.
No, Fortnite will never die.
Oh, I think he's right.
Those can do it for
You guys, one day Snapchat will die. One day someone will listen to this and say like, wow. No, but Facebook hasn't died, but Facebook used to be the high school social media platform. Yeah. And then your younger generation will have something, and you'll look at them and say, this is so stupid, I can't believe they're doing this. And they'll be like, Dad, you just don't understand. You're just not as technologically as adept as we are. Like, your kids will have like implants in their heads that will record every moment and live stream their entire lives, and you'll be like, oh my gosh, it's like, do you guys not care about privacy? And they're like, no, why would we care about that? And you will be all freaked out about privacy. And then we're going to look at you guys and be like, you guys never cared about privacy. You broadcast your lives on your Finstas and think that it's actually still secure. Because the second Instagram gets hacked and all your stuff's out there, you're like, oh, dang it. Probably shouldn't have posted that burning of the book or whatever. That's a reference to something that happened many years ago. You guys don't know about that one?
There was Finstas many years ago?
Wait, someone did that for how many people are watching?
Sorry, we're going to pause on this. No, I'm not going to pause on this rant. Olivia, Beth, I hope you're laughing or something. Okay, let's later. We'll get there. Couple problems left. Okay, let's go ahead and substitute this in. Guys, derivative of the integral. So what I'm going to do is I'm going to take this and actually just plug it in. I get 5 times x plus x squared minus 1. But I need to make sure I multiply that by
dx.
1 plus 2x.
Okay.
So that's fair enough. I mean, if I kind of multiply that, I get 5x squared plus 5x minus 1, which really can't be factored, and 2x plus 1. This just makes it look somewhat symmetrical. Both descending order polynomials that are simplified, but that's about it. No, you do not have to multiply them out.
Multiply it by 1 plus 2x.
Yeah.
Chain rule.
Chain rule. Derivative of x plus x squared is 1 plus 2x. If you have an expression as one of those. So, to generalize on that, let's say that I have the derivative of a times, we're going to call this u of x, f of t dt. So it's not a u, it's a function of u, or dt I should say. This is equal to f of u of x, but then times what?
Times
I know.
We'll say u prime of x. Yes, Elise?
I think we need to go back because no one understands how you got that answer.
I understand.
Elise, you can just ask your question and then I'll answer it to the best that I can.
Okay. I don't understand how you got the answer, and I've heard other people also laugh.
Okay, but let's just go to your question. What do you understand here?
I don't understand the 1 plus. I really don't understand.
Okay. Let's go back to this problem then. If I have the derivative from negative 50 to x of f of t minus 1 dt, do you get that that is going to be the same as 5x minus 1?
Yeah.
Okay. Now, do you get that this right here is the same function that that was plugged in?
Yeah.
Do you get that chain rule says that because I am taking a derivative, I also have to take the derivative of anything that I'm plugging in. So I have to do the derivative of the x plus x squared as well and multiply that.
So like in the previous problems, like I think I got.
So in number 2, that's why I multiplied by the 3x squared. The 3x squared is the derivative of x cubed.
Oh, okay. Got it.
My question did not get.
Did you get it or?
Oh yeah.
Okay.
Yes, sir.
Moving on. The derivative with respect to x of the integral from negative x cubed to 1 of 2t minus 1.
What is that? 2t. What is it going for?
Yes. Okay. Yeah, I reversed them deliberately. Can you undo that? Yeah. Make a problem that you don't know how to do become one you do know how to do. Pull the negative out. You can now switch your limits. Now we can do a substitution and a multiplication. So the substitution would be 2 times negative x cubed minus 1 times the derivative of negative x cubed, which would be negative 3x squared. Keep track of your negatives, and what you should get is a negative 2x cubed plus 1 times 3x squared, which would probably be how I'd leave it. I factored a negative out of this expression, which would give me 3 negatives that were multiplied. You're going to find that leaving, like, you'll either see these things as 1 minus, or well, if they're both negative, you almost always factor the negative out, just so you can see the expressions. You're just going to see that a lot more. You'll see it like this, negative 3x squared times 2x cubed plus 1. Because the question is, you would never just multiply that negative back in if it were like given like that, so you might as well pull the negative out and leave it. So this would probably be how you'd see the final.
Wait, what? Would you put it back in to make it like 6x?
No, you wouldn't put, I mean, you keep things factored whenever possible. And if this, my point was that you would never see it as negative 2x cubed minus 1. without that negative. You'd pull the negative out, or you would see it with the negative there. So you need to kind of know that when you're listing your options. Okay, number 5, derivative with respect to x, integral from negative 2x to x cubed of 2t dt. And I'm going to pause this video for a second to give you guys time to do this and not drive my viewers nuts.
Alright, book story.
And by viewers, I mean like viewer.
Wait, why is your...
So on this problem, we're going to be wise to pick a constant that's in the middle of those two. On the board, I just wrote down as 0. For these notes, I'm actually going to use just a constant letter a, just to pick anything, because it won't matter. But I'm going to make this the derivative from negative 2x to a of 2t dt plus the integral from a to x cubed of 2t dt. These should both be dt's. The reason you're allowed to do that is because you're literally just adding areas. Like you're saying the area of one plus the area of the other is equal to the area of the total. Now this left one we can switch because my second fundamental theorem works when I have a constant as the lower limit. So we're going to go from a to negative 2x and pull a negative out and make this 2t dt plus the integral from a to x cubed of 2t dt.
Did you hear what I just said? I'm sorry.
Here. Okay, keep going. Keep going. So then we get negative. I'm going to plug it in first. So 2 times negative 2x. We're also going to take the derivative of the negative 2x. Don't forget that part. Times negative 2. Plus. And we're going to plug this in. 2 times x cubed. And do the derivative of that. 3x squared. And then we just have to clean up what's left. A negative, this is going to be 8x plus 6x to the 5th. And because we do tend to factor these things, we're going to factor and put these polynomials in descending order. So I'm going to pull out a negative 2x, or just a 2x from that, and get a 3x to the 4th plus 4. It just takes a little bit of accounting to make sure you've covered everything. But as long as you switch, make things negative where you have to. The general rule for this, and it's probably a little bit of a shortcut, is if I have the derivative with functions as both of my limits, you can do f of g of x times g prime of x minus f of h of x times h prime of x. Basically substitute the top one in, take its derivative, then subtract substituting the bottom one in, take its derivative. Okay? I'm going to stop recording now. That's it.